Welcome back to our AI Teaching Machine Learning System Design series. The problem is to design a system that predicts the churn probability of users in a mobile app. Here are some good questions to ask in the requirement clarification phase. What is the business definition of churn for this app? What's the primary goal of predicting churn? How will predictions be acted upon? Do we want to predict churn for all users or specific segments? What user interaction data is available? To frame churn prediction as an ML problem, we start with the inputs. User activity data like number of sessions, frequency of purchases, streaks of consecutive logins, or detailed clickstream behavior. We combine that with static features such as demographics, device type, or geography. Crucially, we leverage historical labels, whether a user churned or remained active, which makes this a supervised learning task. The output is a probability that a user will churn within a given horizon, often defined as being inactive for 30 days. This probability allows us to rank users and apply interventions at scale, adjusting thresholds depending on business costs and benefits. This is fundamentally a binary classification problem with probabilistic output. Now, let's talk about the modeling options in detail. Logistic regression is the simplest baseline. It's interpretable, easy to implement, and provides feature weights that help explain churn drivers. However, it struggles with nonlinear feature interactions. Tree-based models like XGBoost, LightGBM, or CatBoost are industry workhorses for churn. They handle tabular data well, automatically capture nonlinear effects, and often deliver strong performance with relatively low training cost. Neural networks, MLPs, can model richer feature interactions and work well when you have dense embeddings of categorical variables like user IDs or item IDs. For sequential event data, RNNs, GRUS, LSTMs are natural candidates because they capture patterns in user activity over time, such as gradually decreasing engagement. Transformers push this further. They can process long interaction histories with attention mechanisms, learning which past behaviors matter most for churn. This is especially relevant in apps with complex or diverse user journeys. In practice, many systems use hybrid approaches. For example, embedding user activity sequences with a transformer, then feeding those embeddings into a gradient boosting model for the final churn probability. Finally, the prediction horizon must be carefully defined. For daily use apps like gaming or social media, churn might mean inactive for 7 to 14 days. For less frequent apps like banking or travel, churn horizons might be 30 to 90 days. This definition directly impacts the quality of labels and the usefulness of predictions. Before modeling churn, careful data preparation is critical. We start with the label definition. Churn must be precisely defined, usually as no activity for n days. A common choice is 30 days, but it should match the natural usage pattern of the app. For example, a gaming app may use 7 to 14 days, while a finance app might use 60 to 90 days. Defining this clearly ensures consistent labeling. Next comes feature engineering, which is the backbone of churn prediction. We design behavioral features such as how often users log in, how long they stay per session, their purchase history, and in-app actions. User profile features like demographics, device type, or subscription tier add further predictive power. Importantly, we look at engagement trends, not just raw counts, but changes over time, such as declining session frequency. For sequential approaches, we can use clickstream or event histories directly. For data handling, we must address missing values, which are common in user data. Strategies include imputation with medians, flagging missingness explicitly, or creating a special missing category. Numerical features may need scaling, and categorical variables can be one-hot encoded or represented with learned embeddings, especially if the cardinality is high. A major challenge is class imbalance. In most apps, churners are fewer than retained users. This imbalance can bias models toward predicting no churn. To address this, we can oversample churners, e.g., smote, undersample non-churners, or adjust class weights during training to penalize misclassification of churn more heavily. Finally, when splitting data, we should use time-based splits to mimic the real-world scenario, training on past data and testing on future data. This avoids data leakage, where future behavior accidentally informs the model. Getting this right ensures our evaluation metrics reflect production performance. We begin with classification models, which are the most common starting point for churn prediction. Logistic regression is typically the baseline. It's fast, interpretable, and outputs a probability directly. For instance, if we include features like average weekly sessions or days since last activity, the coefficients can directly tell us whether increasing that metric increases or decreases churn risk. However, it only captures linear relationships, so its predictive power is limited. Next, we move into tree-based methods. A single decision tree creates intuitive rules but tends to overfit. Random forests solve this by averaging across many trees, making them stable and robust. The most powerful category, however, is gradient boosting models, such as XGBOOST, LightGBM, and CatBOOST. These are widely adopted in churn prediction pipelines because they handle missing values naturally, e.g., unreported demographic fields, handle categorical variables, e.g., app version, device type, and capture nonlinear feature interactions like users who recently reduced their session length and haven't purchased in 30 days are at much higher risk. In production systems, we often calibrate probabilities since business teams need accurate churn probabilities to guide retention campaigns. Models like XGBOOST can be paired with Platt scaling or isotonic regression to ensure probability outputs are trustworthy. Ensembles further improve performance. For example, stacking a logistic regression on top of random forest and XGBOOST predictions. The advantages here are clear. These models are interpretable, computationally efficient, and extremely strong on tabular data. The main limitation is they rely on engineered features and cannot natively capture sequential dynamics of user sessions or event histories. To overcome this, we consider neural networks. When predicting churn in mobile apps, neural networks truly shine when user activity is sequential, since simple classification models can't capture temporal patterns well. We start with RNNs. The most widely used are LS, TMS, and GRUS. LSTMs use a system of gates, input, forget, and output, to control how much past information is carried forward. This allows them to capture long-term dependencies. For example, if a user's engagement slowly decreases over several months, an LSTM can learn that this gradual trend is predictive of churn. GRUS are a streamlined version with fewer gates and parameters, often faster to train but still effective. For shorter session histories, like 7 to 14 days of activity, GRUs may actually perform just as well as LSTMs. Some systems even use bidirectional RNNs, where one layer processes sequences forward in time and another backward, capturing richer context within a user's recent sessions. The main drawback is that RNNs are inherently sequential in training, which makes them harder to scale, and they still suffer from vanishing gradients with very long histories. Transformers solve many of these challenges. Instead of passing information step by step, transformers use self-attention, which lets every event in the sequence attend to each other. For churn, this means the model can relate a user's first week of activity to their most recent week, even across hundreds of events. Positional encodings ensure that sequence order is preserved, since self-attention itself is order agnostic. In practice, transformers are much more scalable because they process sequences in parallel, making them suitable for very large user bases. Variants like BERT-style encoders can summarize a user's historical behavior into a representation used for churn prediction, while GPT-style decoders can be used autoregressively to both predict next actions and infer churn risk. For extremely long event logs, thousands of clicks, efficient transformer variants like longformer or performer can reduce the quadratic attention cost. This makes transformers state-of-the-art for user retention modeling at large tech companies like Netflix, TikTok, and mobile gaming apps. Finally, hybrid approaches combine the best of both worlds. Wide and deep models balance interpretability with complexity, while multimodal neural nets merge tabular demographics, categorical features, and sequential activity streams. This allows the churn prediction system to make use of all available signals, not just static profile data, but evolving behavioral patterns. Evaluating a churn prediction system requires both offline model performance metrics and online business impact metrics. Offline, we begin with standard classification metrics like AUC ROC and precision recall AUC. Since churn is often an imbalance problem, maybe only 5 to 10% of users churn monthly. Precision and recall are often more informative than accuracy. F1 score balances the two. Beyond classification accuracy, we also need calibration. If the model says a user has a 70% chance of churning, then around 70% of those users should actually churn. Breyer score and reliability plots help validate this. From a business perspective, we also measure lift and top K recall. For example, if we can identify the top 10% of users most at risk, how many actual churners do we capture? This directly impacts how efficiently marketing teams can spend their intervention budget. But offline evaluation is not enough. Online A/B testing measures real-world outcomes. The key metric is retention lift, how much lower churn is in the group where interventions are guided by the model compared to a control group. Secondary metrics include engagement, like DAU/WAU/MAU ratios, or average session frequency, and revenue impacts, such as increased lifetime value or higher subscription renewals. We also look at the conversion rate of retention campaigns. For instance, how many high-risk users actually respond to discounts or push notifications. Human evaluation also plays a role. Marketing and product managers may review flagged high-risk users to ensure the predictions align with their understanding. This feedback can guide whether we should prioritize precision, minimize wasted campaigns, or recall, maximize captured churners. Interpretability tools like SHAP values help explain why the model predicts churn, such as declining session frequency or reduced purchases. Finally, we evaluate operational aspects. Predictions must be low latency to trigger timely interventions, e.g., sending a push notification within hours. The model should also be robust across user subgroups. What predicts churn for a brand new user may differ from a longtime subscriber. And we must monitor fairness, ensuring interventions do not unintentionally discriminate across demographics or user cohorts. This multi-layered evaluation framework ensures that the churn prediction system is not just accurate, but also actionable, trustworthy, and impactful for the business. Deploying and serving the churn prediction system requires careful engineering to make predictions actionable in production. We begin with model deployment. Once the model is trained and validated, it is packaged, often using Docker for portability or ONNX for framework interoperability. The model is then deployed as a REST or gRPC microservice that the app backend or marketing systems can query. To ensure smooth operations, we use a CI/CD pipeline that automates updates, supports canary rollouts, and allows fast rollback if a new model underperforms. Next is model serving, which can happen in two ways. For batch serving, we might compute churn probabilities daily or weekly for all users, storing them in a database for marketing campaigns. For real-time serving, we predict churn risk dynamically when new behavior signals arrive. For example, a user suddenly reduces app usage or cancels a subscription trial. Many companies adopt a hybrid approach, batch predictions for the entire population, plus real-time updates for high-value or high-risk users. Latency is critical here. Predictions must be served in under 100 milliseconds so that push notifications or interventions can feel instantaneous. The model's predictions then need integration with business systems. For example, churn scores can be fed into a CRM or marketing automation tool, triggering personalized retention campaigns like push notifications, special discounts, or targeted emails. Additionally, dashboards are provided for product and marketing teams to visualize churn risk distributions and monitor which segments are most vulnerable. Once deployed, the model requires continuous monitoring. On the technical side, we track prediction latency, system errors, and throughput. On the ML side, we monitor model performance and calibration, making sure predictions remain accurate as user behavior evolves. Data drift detection is critical. If a new app feature changes usage patterns, the model may no longer generalize well. Finally, we monitor business impact metrics, such as retention lift and campaign ROI, since even a highly accurate model is only useful if it drives meaningful improvements. To keep the model fresh, we adopt a retraining strategy. Typically, the model is retrained on recent user data weekly or monthly. A champion-challenger setup can be used. The current production model is the champion, and new candidate models, challengers, are A/B tested before rollout. This ensures that we only promote models that demonstrably improve outcomes. A human-in-the-loop process helps validate new features and ensures campaigns driven by the model remain aligned with business strategy. In short, effective deployment and serving ensure that churn predictions are timely, actionable, and continuously optimized for both accuracy and business impact.